Good evening and welcome everybody. This is Obi-Wan Pez for N Simplex Pachinko. We are working on night 7 of our differential equations class. And with me tonight we have e to the 2I pi is Zach, and we have enstucky. If you would introduce yourselves.
I'm enstucky. I normally stream on Twitch, but I've been taking an extended vacation. Here to get back into the DE swing of things.
And I'm Zach, also streaming under e to the 2I pi. I am currently helping out with this class, or like trying to talk through stuff again, and stream on Twitch as well. And yeah, we're having a good time doing some DEs.
And I would like to thank both of the co-hosts for putting up with me. So it has been an interesting time. Hasn't always been the easiest to know what it is that I would like people to say. And of course, I did not get this screenshotted before we actually started that. So sorry about that.
Good.
Maybe next time I'll have it down. All right. Here's to hoping. Tonight, 8-5, and here we go. All right, so as we said from last class, we were talking last time about steady state vectors, and we had a system. I have the equations right here. X prime is equal to 3x plus 2y, and y prime is equal to x minus y. We had discussed the ability to find steady state vectors, and we were looking at the phase plane system, which I have right here. Let's put that here. Okay, now this is pretty messy. We kind of get the idea that we were talking about from before. Zach, do you want to maybe walk us through what we had talked about?
Let's see how much I remember. Okay, so we had some vectors. The phase plane here is all the arrows pointing in their respective directions for different points on the phase plane. We made the purple, those are purple, right? The purple trajectories.
Yes.
And those are the specific solutions for given initial conditions. And we determined that these vectors are gradually tending towards this green vector along the line, and I'm guessing this is the line y equals something x. Like it looks like a fourth.
Yeah, we had a reasonable approximation for these vectors.
Yeah.
We'll get to what those actually are a little bit later.
Right. So the number, I suppose, is unimportant, but the purpose here is that we have a direction that all of the solutions seem to tend the in some way. And there's also a vector that is mostly in pinkish red or whatever, that the curves are emanating from, which are along this y equals minus something x, which we have yet to determine what that is.
Right. And
so
I won't, put too much suspense on this. This was very approximately y equals negative 2.2x, and y equals 0.2x. Again, very approximately. This was just off of this diagram, so we're hoping that's right, but we'll see.
Okay.
Anything else you want to add?
I mean, I'm trying to remember if there's anything else we discussed, because it's been a week.
Right.
But I think that's the idea that I remember leaving on.
Right, and so we did talk about the fact that these steady state vectors, if you ended up starting at any particular point on, let's say, on one of those vectors like here, then the direction of travel that you end up moving on from that point ends up being a constant multiple of the vector that gets you from the origin out to that initial point. So we had talked about that in the context of our system of equations over here, or system of differential equations, in matrix mode. So we switch this to xy prime is equal to an A matrix, which is a transformation matrix, 3, 2, 1, -1, which contains all of the coefficients of our system times our variable vector xy. Okay, so we said here that a lot of times this is going to be like x vector prime is going to be equal to a times x vector, and so really some little vectors should be put over our x's here, but I am using OpenOffice and it doesn't have that, so I'll just put them in now.
The OpenOffice struggle is real. I understand.
It's very limited, but hey. All right, so we said from here, our original system x prime, or x vector prime, is equal to a times x vector, is going to represent our system, and we want to know where these particular steady state vectors are going to be. So how do we go about talking about those steady state vectors?
So if we have, I mean, it looks like we were observing that these lay on lines that were starting at the origin. So if we were to do something like set y is equal to mx, to sort of go along with that assumption, we could see what happens to the differential equation of the system.
Okay, how would you propose to do that?
Well, yeah, so set y equals mx, so we get the top would be x prime is 3x plus 2mx. The second one is going to be y prime, which is mx prime, because we can just move the constant out. It's equal to x minus mx.
Let y equal some constant times x. Alrighty. And yep, y prime. Nope. Okay.
So now we have two, I guess those are separable equations, so we could probably solve them and see what we get. 3 plus 2m times x. I guess at this point we probably can just say that That's an exponential solution.
Okay, we can also, I think you had wanted to factor, or was that no?
Yeah. Get it in that next separable form.
Right, and this one's going to be mx prime?
Yeah.
Right, so in both of these cases, we're going to end up with x prime of x is equal to, over here, 3 plus 2m. And either we can make this dx, and this is just going to be... Well, we didn't really discuss that, but in this particular case, we would say that the independent variable is going to be t, generally speaking, unless otherwise specified. Both of these... Yep.
No, sorry, well, this is just going to be an exponential solution, though, because we have a function whose derivative is itself times a constant. And so this is your e to the kt solution. Right?
Yep, so we can also do that. So we could go about it either way that we want to do this. Again, this top one here is going to end up being sorry, we're going to end up using, in this case, separability. And in the bottom case, this is just a first order linear. All right, and so
now correct me if I'm wrong here, but that factor m minus 1x, I think that's the reciprocal of m minus 1x. I'm not. Are you dividing by m?
Which one here? Yes,
yeah, the second one.
Because I did divide by m.
Yes. Yeah, I just want to make sure.
Yep. No, that's definitely definitely what I did, even though I didn't write it. Right. So in this particular case, we're just kind of assuming that we've got a mu, which we talked about earlier, was going to be our integration factor. And again, that was one of the key vocabulary words that I didn't actually mention when we went over it, but typically we talk about integration factors in differential equations, and that's just the thing you're multiplying by to make the integration anti-derivation much easier. So in this case, that's going to be e to the... And yeah, we could either make it just 1 minus 1 over m, or m minus 1 over m. Dealer's choice, really. So we're going to end up with x times e to the m minus 1 over m, parentheses, is going to be equal to 0, and so this is going to be equal to a constant, and then it's going to slide over to the other side. Alrighty. T. Sorry. That's kind of important. Or wait. Yes. That'll be fine.
Yeah, looks good to me.
Okay. So this is our x solution that we got here. Now what?
So that was the second equation, right?
Yep.
Well, so from the first equation, what we're gonna get x is equal to c e to the d, maybe e to the 3 plus 2mt.
Right, because we could do the same. We could do the same thing with this one if we wanted to do first order linear instead. Right, x prime minus 3 plus 2m x equals 0. So then we're going to get mu, in this particular case, is going to be equal to e to the negative, parentheses, 3 plus 2m t. And so we get x e to the negative, parentheses, 3 plus 2m t, all prime equals 0. Integrate both sides, gets rid of that stuff. And in this particular case, is this c going to be the same as the other c?
At this point, I don't see any reason why that's true, although we might be able to argue that by plugging in some initial values.
I wonder if we chose, excuse me, because we know this is the line y equals mx, we should be able to put in also the point 0, 0 in here, yes?
Should work for what?
Or work for any line we choose, because they're on the, your line goes through the origin, that should always be a point on the line, yes?
For what values?
The 0, 0.
Right, 0 for what values?
Oh, sorry. So you'd want to put that in for, since we assumed y equals mx, that would be for x, and for mx. It would need to be 0.
Yep.
So our x value would need to be 0 here. Also, I'm not hearing the dubstep Phobos, but hey. I have Obi's stream technically muted. I have just on the voice call here unmuted, so I can't hear the awesome music. But so I'm jealous.
All right, so what's our goal?
Well, we want to know the value of m.
I'm sure it's an interesting mix, Fembox. So if we plug in 0, 0 for x and y in this particular setup, then what's going to happen?
We're going to get c is equal to 0.
Right, c is going to have to be equal to 0 in both of these equations in order for us to actually have that happen.
Yep. So it's not like, I suppose, the most helpful thing, but nonetheless, it is something that is true, that we made the assumption that the line that these eigenvectors, I mean, I'm spoiling a little bit, but like these eigenvectors are going to go through 0, 0.
Mm-hmm. And if we're at 0, 0 itself, what's going to happen to the whole system?
Well, it's going to hit an equilibrium point.
Which
Right,
means
so
that
we're not going to go anywhere.
Right, which means that no matter what our eigenvectors were, no matter what these steady state vectors were, all of them end up getting spoiled at 0, 0.
Mm-hmm.
So it didn't actually matter what we were doing here in terms of like all these individual steps. If you assume that you want to talk about the point 0, 0, no matter what system you're in, it's just going to end up not working. So, important step. Not actually where we want to go, though.
I get it. I get it. So the other thing that's important is we want to find the slopes. So that means that we have to somehow, we want these two things to be equal, yes?
Mm-hmm.
The left and the right, the thing in orange and the thing in blue, we want those two things to be equal.
Okay.
So since we're talking about the same line, because I haven't done it this way, so I'm trying to reason through this in real time now.
Mm-hmm. Yep, that's fine.
But I think what would happen is that the C's would be the same because you're on the same line. You're going to have the same thing. So everything. So then you can try to solve for M based on your two solutions.
Alrighty.
And that turns into some kind of quadratic, which actually, if I'm honest, we didn't need to do all this algebra to solve the equation at all. We could have just started back on the system and just solved for M directly.
So if we try it anyway, right? Just
if we try it, yeah. I mean, we should try it, but
right, in this particular case, we're gonna, yeah, I mean, like you said, I don't even know if we're just gonna bring everything to one, or all the constants to one side and all of the e's to the other. Let's keep the 2 positive, maybe? 2m. So that's going to be C blue over C orange, which now just becomes some C.
Just do like a C brown. I don't know. Orange was blue. I don't know if that's brown or not, but that'll work.
And then we get like 3 plus 2m, and in this case we're going to subtract our exponents from each other. So 1 minus m over m all times t. Okay, so here we're going to get a 3, and then from over here we're going to have a negative m divided by m, and then the negative out front of it, so that's going to be plus 1. And a plus 2m minus 1 over m, which the t is equal to some constant. Okay. So to solve that one, take the log, because quite frankly I don't want to deal with that. This is going to be 2, well, okay. 2m minus 1 over m, and it'll be fine. Plus 4 is equal to natural log of c is, again, some constant. So we could keep backing this up as much as we want and just call it a constant. It's going to be slightly different, but quite honestly, right, it doesn't much matter what we call it, it's just going to be a constant. Some people might not like that, but All right, if we shift stuff around, let's multiply by m. So we do get 2m squared minus 1 is equal to km. And so that's going to be a 2m squared minus km minus 1 is equal to 0. Right. So at this point, we do end up with a quadratic.
And that can just be thrown into the quadratic formula.
Right. So our m is going to be equal to... Welcome back, Kogel.
Let's see here. K plus or minus, what is this? K squared plus 4 all over 4. Something like that.
Sorry, what did we do?
I was solving for solving for m in terms of k. That's all. I was just applying quadratic formula to that. So
okay.
K plus or minus. Let's see here. What did I say? K squared.
Yep.
Plus 4 all over 4. Just
right.
Now, just a second.
Ooh, wait, that extends.
Plus 8, maybe?
Yes. Thank you. Okay. So with what we have here, what kinds of solutions are we going to get?
So the radicand is always positive, yes, because we'll have a decay. No matter the value of k, that will always be positive. So these will always be real solutions.
Right.
Right, so they're always going to be real, non-complex in this particular case. Colgold says one solution is certainly going to be negative. Why? Or is it always true?
One solution is going to be what?
Number theory wise, you have the fraction up top there, k plus or minus the square root of k squared plus 8. Is it true, as Cold Gold says, that you're always going to have, no matter what the k value is, one that's positive and one that's negative?
Yeah.
All right, why?
K squared plus 8 is, well, radical that is greater than k.
Yeah, I was just about to say that. Thank you. As you were saying it, I'm like, that's exactly it.
Mm-hmm. Yeah. So in this particular case, yeah, we're just always going to get, right, the radical of k squared plus 8 is greater than k itself, and so the k plus that thing, even if it's a negative number, right, the radical is always going to win. So that's just always going to end up being positive, and then if k was negative, we have the negative version. So that sends it off in the negative direction. And then if we assume that k is positive, then the positive one remains positive, but the negative one is going to have a larger radical piece that's dragging it negative. So yeah. Right, that is actually one of these things that's really important to discuss when you're trying to figure out like what kinds of behaviors are going to exist on this phase plane. So even if we didn't know what the k value is, like there's no way to figure it out, we don't have a phase plane for the system for some reason, you know, we have no other analysis tools, we could still go through this process and say, based on this quadratic that we came up with, our m value is always going to have two real values, and they're always going to be of opposite signs.
Well, and this is significant because we noticed in the phase plane that there was a line that points sort of outward, if you will, like that points positively, and then there's a thing that points inward. So you have this sort of inward motion towards something, and you have an outward motion away from the origin. That suggests this positive-negative relationship that we're talking about.
Yeah. So we were talking about how when you're just looking at the steady state vectors, if you were to start exactly on one of them, then again, what's going to happen is we get this multiple of whatever the vector is to get to that location. And so in this particular case, we're also looking at those m values, wink, wink, nudge, nudge, which are showing us that here the multiple that you're going to get along the shallow line, so y equals 0.2x, is going to be a positive multiple of that vector because they are also pointing outward from the origin. And so it should consequently and similarly align in the opposite direction, that our alignment with y equals negative 2.2x going this way should have a negative value associated with that particular multiplier. So we haven't technically gone with the names of all the... I guess we brought it up last class, but we just briefly mentioned the words eigenvalues and eigenvectors. And so these are where these things come in. The eigenvectors are going to get you the steady state vectors. Been coyly alluding to them as steady state vectors. Hey, Super Henrik. Welcome on in. And hi, everybody that I didn't mention. I'm sorry. And our eigenvalues are going to be those values that when you start on whatever location you're on, again, you're going to multiply by that eigenvalue to get you the direction of travel, the motion of travel from that point, either towards or away from the origin directly. So this is where it gets kind of really exciting. So we wanted to be able to figure out, like, how do we actually figure all this out? Because this stuff, everything that we did here, can come out with the answer, but we kind of been dancing around it, right? We've had these m values, which then still produced a k value, and we still don't know what those m and k values are going to be based on the original system yet. However, we did say last time, very briefly, that what we're trying to do is get our matrix system, the transformation of that matrix A times X vector, should, if these are going to be eigenvectors, so not X anymore, a generalized XY point, but Xi. I'm sure that's an awful Xi, but nonetheless. So if we use Xi instead and call this our eigenvector.
By the way, I'll give you your C out of 10. How's that?
Thank you. Is going to be the same as taking that same eigenvector C and multiplying it by a constant multiple. So we're going to have that just be a constant. And it's going to be our eigenvalue. All right, so again, A is our transformation matrix. We want to transform Xi, but every time we try to do that, it ends up just being a constant multiple of itself. So we say, oh, this is really cool. These are these particular steady state vectors, and how do we go from here? I mean, I've got it written on the screen, I guess, but... Go for it. Hey, Don, welcome in.
Subtract lambda xi from both sides. Interpret lambda c as lambda times the identity times c, so we can factor out the vector.
And what's left over here?
0.
I mean, a 0 vector, if you like.
All right, our 0 vector has to be the same size as
I saw
other...
the Rye smile on screen. I was like, you know what? He's gonna troll us and say it's got to be a vector.
Yep. So it does have to be the same size as A times C or C itself. It's all the same. All right. So in this particular case, yep, we're gonna say that A C. That's gonna just get terrible over time. It's gonna be lambda times our identity matrix, which is gonna be the same size as matrix A. So we have A being m by m. We shouldn't use m, sorry. N by n matrix. Then I should also be an n by n matrix. All right, times C. It's going to be equal to that same 0 vector. And again, in this particular case, C has to be an n by 1, which means that our 0 vector is also going to be m by 1. If anybody does not remember their matrix multiplication, we can go over it some other time. Okay, then what?
Factor. Factor on the right.
Right, and with matrix multiplication, for anybody who doesn't remember, it's super, super important that you're going to preserve the left and right multiplication, because matrices are not commutable generally. They leave us with a bit of a problem. All right, now with this, what are the possibilities? If we go back to our, basic algebra stuff. Yeah, capital sigmas sometimes vary by...
So you're talking about the A minus lambda I.
Mm-hmm.
So that so the determinant of that needs to be 0.
Why?
Well, because if not, then we don't want the eigenvector, or I guess C, to be 0, because that would be the origin again. And we discussed earlier that the origin isn't very... We don't really want to care about that point too much. So it would have to be that a minus lambda I in some sense is going to be 0.
Right. So here we say, well, this is a trivial case, so
yeah,
that doesn't work.
Trivial.
We already did that over there. We said that's true for literally every example, so it's not special to this particular system. We want something that's special to this system. So yeah, how does a minus lambda I equal 0? Well, in this case, if it were to be a proper matrix, this would need to be a 2 by 2 matrix, which is then equal to all that stuff. But then that means that we've got a minus, if we're just doing a 2 by 2 system, this is going to be lambda 0, 0, lambda. And if it were 0, 0, 0, 0, we can't guarantee that that's going to happen. And in fact, most of the time, it's not going to happen. So it's not going to be a 2 by 2 matrix. However, Zach, you said something very important.
We don't need the matrix to be 0 properly. We just need that it's non-invertible, so that the determinant is 0.
Right. So we want you said we want this particular combination of things, right? A minus lambda I should be non-invertible.
Right, yeah.
Love it, gonna steal it. ABLE? All right, so if a minus lambda I were invertible, then what would that mean for our system here?
It would mean that the C had to be 0.
Right. So then we'd be back to this trivial case where we say, well, that means that C is equal to 0, and we don't want that.
I was about to ask a point of clarification, and I thought I unmuted myself, but I clicked the unmute on the Twitch stream and tried to say something, and that doesn't work too well. So, pro tip.
Did you want to, or did it already get
No, we're good.
covered?
We're good.
Okay.
It's fine.
All right, so in this particular... Yep. Go ahead.
Sorry, no, just like you said, the determinant would need to be 0 of our a minus lambda I.
Yeah. So the... Oh, right, because I asked you. Yep. I got you. Yeah, so we want the determinant of a minus lambda I to be equal to 0 so that, intentionally, we have a non-invertible a minus lambda I, so therefore C cannot be 0 from this thing back up here. Okay. Good times. Do you all also put those in like the absolute value symbols instead of putting determinant sometimes? Or is that different?
So notationally, I usually say, like when I write the matrix A minus lambda I, I'll write the absolute value bars around that. But I don't know if you're talking about for the in what you've written in parentheses.
I just meant that part.
Oh, that part? No. Yeah, I usually don't. Okay. Yeah. I'm sort of with cold gold. That doesn't look right at all.
Okay. That's fair.
But at least for me,
Okay. So we've got a determinant of A11, A12, A21, and A22. If we're just doing a 2 by 2 matrix system, again, we'll keep with that for at least a... Oops, hang on. Yeah. We'll keep with this for a little bit. Okay. Determinant of. So we have our first matrix, and then we subtract our identity times lambda matrix like this. All right, so we get the determinant of a11 minus lambda, a12, a21, and a22 minus lambda. All right, and for those who might have forgotten, how do we do determinants? Two by two determinants.
You multiply the diagonals and subtract the major diagonal, or like I guess you don't call it. I don't know if you call that the major one, but like the one that is positive or the even. I think that's an even permutation, and then the odd permutation. So basically, the top to bottom diagonal and then bottom to top diagonal, if you will, in some sense. I don't know when I think of it. That,
I mean, it makes sense to you, right?
yeah, it makes sense. I'm trying to just say that the first and fourth entries and the second and third entries, you subtract the products.
Okay, and so we can see here this is going to be lambda squared minus parentheses a11 plus a22 lambda plus a11 a22 minus a12 a21. All right, we looking okay?
That looks reasonable.
Right,
now,
so, yep.
Is this a place where I can insert something? I don't know if this is OP right now.
Go for it.
But if you look at the way you've written the general quadratic, the a11 and a22 is the sum along the diagonal. And we usually call that the trace of the matrix.
Okay, from linear algebra.
And then the thing on the right, you've got the a11 and a22 and a12 and a21. That's basically the determinant of the matrix. And so you're getting the trace here in your linear term and the determinant in your constant term. Just sort of a fun fact. I don't know if you wanted to bring that up now or you're going to be going there or whatever.
I wasn't originally. No, that's interesting.
That's sort of a fun fact.
So it's you're subtracting the two. Right, you're subtracting the sum of the main diagonal of A. Okay. Yeah, I wasn't gonna go there. That's not in my notes, but
well, now you know.
Woohoo! Right. Okay. So in this particular case, now we've got something to work with for the quadratic, and for any like normal system that we're talking about at the beginning here, we're going to have numbers for all of these A matrix, like the transform matrix values. So all of our A's with subscripts are just going to be numbers, which means this is now a quadratic that's quite easily solvable. This was the... Right. This was going to be 0. Right, we want all of this stuff to be equal to 0. Which means we've got lambda is equal to, and we'll just kind of go from here real quick, right? A11 plus A22 plus or minus the square root of that same thing squared. Minus 4 times A is 1, and it's always going to be 1, so that makes it kind of nice. Times C is going to be our determinant of the original A. Again, A11, A22 minus A12, A21. And now all of this ends up being over 2. Again, times 1, because our original A value that's sitting out in front of lambda squared is just going to be 1. And again, this is always the case, so it makes it kind of nice. With what we had up above, we had the original matrix was 3, 2, 1, negative 1. Oops. What are we going to fill in for these? Am I in the way? No, we're good.
2, 1, negative 1. So the trace here is going to be 2. And the determinant is negative 5. Negative 5, yeah.
Okay, which in this case, we get 2 plus or minus square root of...
Negative 5.
For the determinant, yeah, negative 5.
Gotcha. Which is?
24?
Yeah.
2. We can get a 4 out of that one. Leave behind a 6. So 2 plus or minus 2 root 6 all over 2. Hooray! So our lambda for this particular system is going to be 1 plus or minus the square root of 6. Alright, so where does that leave us?
Well, originally we wrote down that where the lambda showed up. I guess we could go way back to the beginning. Is that where we want to go?
So let's look at it more from the same algebraic perspective we were looking at it from before when we tried it the other way. We got our k or m values down here in terms of k. So I guess are the properties that we found still holding?
We did get real eigenvalues here, or real lambdas. And we did get a positive and negative. Because square root 6 is bigger than... The magnitude of square root 6 is bigger than the magnitude of 1.
Right, so we got real and opposite signs for our two possible solutions. Again, the relationship that we found still holds from before, so that's looking promising. What other possible solutions could we get for lambdas? If it wasn't this particular system, if it ended up being just any system.
I mean, you could get complex valued things.
All right, if we turn it back into old terms of our quadratics, we're just saying that the old b squared minus 4ac thing splits into three different possibilities here. So we could get, shouldn't even put equals, but whatever. Right, we get the ones that are greater than 0. We end up with two distinct real eigenvalues. If we get it equal to 0, we end up with what?
We'll have this single real.
What's special about it being single?
Well, geometrically, we wouldn't have like that cross that we had in our picture before. There would only be one direction. That things were tending to or away from.
Geometrically, in terms of a quadratic, what's happening?
The two solutions are merging.
Yeah. Oftentimes people just say that they're, repeated values, repeated solutions. All depends on what your teacher was feeling that day, really. All right, in the case of real eigenvalues, we already saw that there are a couple of different ways that this works. So the ones that we had, we saw an example of opposite signs. Where, again, one side was coming in while the other side was going out. And I know the case we have is actually opposite this, but it's all good. And how is this going to affect the system overall?
Well, you're going to have things pointing outward, like things gravitating outward, if you will. Your solutions won't bend the same way. So you know how you bend towards the origin, and like you have like this hyperbolic behavior. You'll have two solutions that will basically you'll gravitate towards one of those directions. I'm not doing a great job because I don't have pictures.
No, I understand. The outward-facing eigenvectors are really going to be, or the outward-facing eigenvector is going to eventually be the direction of travel. Yeah.
And specifically, because these tend to be exponential solutions, because we have these are really two single variable, or two. The solution is a linear combination of exponential things. The thing with the larger eigenvalue is going to tend to dominate behavior. especially if you have positive things, right?
Yes. Okay. Yes. And larger in the sense of magnitude, or larger in the sense
magnitude.
of... Okay.
Right. So the thing that has the larger, so for example, if you have an eigenvalue of 5 and 10, the 10 is going to win. Right. The thing that was associated with magnitude 10 is going to matter more than the one with magnitude 5.
Okay. Matters more does not necessarily mean win.
I say win in the limit. I should be precise here. That the limit is, as t goes to infinity, it's going to be, it's going to dominate. Win in the sense of larger than. Something with e to the 5t or e to the 10t as t goes to infinity, e to the 10t has a stronger pull on your curves.
Okay. However,
that's what I'm trying to say. I didn't say that properly. This is hard to do even with just voice call. Like I can't even draw stuff. So I mean, this is hard.
Yeah.
I could go on Excalibur. I guess that's true. So I shouldn't complain. I just have my piddly mouse.
Yeah. No, I get you.
So
yeah, I was gonna say there's kind of a slight bit of a difference if you end up having opposite signs, right? What's happening to the thing that's going towards 0? Probably just gave it away, but
I was gonna say, when you're saying and the thing, I mean, I guess I need an antecedent to the thing.
So if you have an eigenvalue which is negative, and let's say it's even negative 50 or something like that, and then you have an eigenvalue that's positive 1, you got something that's going like this. What is going to happen as t goes to infinity?
Well, go ahead.
Solutions are going to point in the direction of the vector associated with 1.
Right. So they're going to go toward the... In this case, it wasn't even... Right. Yeah. It's not even the one that is the larger magnitude. It's the one that has the larger number.
The larger.
And
the large... Yes. Thank you.
Right. And if it's positive, then it will follow that one off to infinity. If they're both negative, we got some interesting interplay, and we can talk about that some other time. Well, I mean, coming up next, but... So, when you have opposite signs, you end up following, again, follows the positive eigenvalue as t goes to infinity. Positive infinity. Should probably stress that. So when you have same signs, what's happening? We don't have to be particularly specific, but
Yeah, I mean, I guess the larger of the two values is telling you what direction your solutions will be pointing toward as t gets large. And if they're both negative, where maybe it points in the opposite direction. I have to think about that. But
and thinking about it is the main goal, of course, right? For any of the students who are taking differential equations either now or in the future, watching this back on VODs or anything like that. What we really would want you to do is play around with different systems, see what eigenvalues and eigenvectors they have, and eventually try to figure out some sort of pattern that exists. me just giving it to everybody is, you know, I can somewhat understand kind of how it all works, but at the same time, like, it's no substitute for playing with it. Right, so if they have the same sign... Yep.
Well, I was going to say, if they have the different signs, something, if you are playing with it and you're watching the VOD, something to keep in mind is that if you have things that, if you have positive eigenvalues, you're going to expect sort of this approaching the larger eigenvalue, right? But if you go the other way, it's going to be, you're going to get some stability of some sort. And I'll just give that out. I'll throw that out there for those who are watching this later. If you're needing a hint, think about stability versus instability and why that would, or unstable points and so on, and why those would happen. So I'll leave it there.
And generally speaking, if we're just talking about the eigenvectors themselves, if they're both positive, what's going to happen to things that are on them? So we put a particle directly on one of the eigenvector directions. What's going to happen?
Well, it just stays there, right? You just stay on the line.
How do you mean stays there?
You're traveling in the same direction.
Okay, and which direction is it going to travel?
Right. Well, it depends on which eigenvector, but if you're on the eigenvector that, like, if you're on the dominant eigenvector, you're going to stay there, right? And by dominant, I mean the larger eigenvalue associated.
So when we talked about eigenvectors, right, they themselves, I used a separate set of words. What was it?
I actually don't remember, to be honest.
Sorry, it's up here.
Trying to understand what your question is.
So we were saying, I was calling eigenvectors something else at the beginning.
What did you call it? You called it the steady state vectors.
Right. So regardless of which eigenvector you're on, what does that mean?
Well, they're both steady states. I mean, they're so both vectors are steady state vectors.
So what does that mean? Sorry.
It means that you're anytime you're on that vector, any point on that vector or any vector on that vector will just be scaled, and therefore the direction of travel is the same.
The same as
where you were before. Like, it's the same.
Okay.
You're pointing in the same direction. Steady state meaning that there's no change in direction.
Okay, so if you're on one or the other of the vectors, what about the other one? So I'm just comparing what you'd said earlier with what you just said now.
Well, the other vector is so say you're on the non-dominant eigenvector. Then when you're on that vector is also a steady state vector.
Mm-hmm.
And so any point along that vector, you're going to stay pointed in that direction.
Okay.
And so there's no, like, gravitation, right? Like, you're already there.
Mm-hmm.
You stay on that vector because that's exactly what steady state means. And so in a sense, that line becomes its own solution.
Yeah, so essentially, right, your path is going to remain on that particular vector. You're never going to deviate at all. So earlier when you'd said like your, it depends on what the other or dominant eigenvalue is going to be.
Well, I mean, it's that these are these. Again, this is something I don't get to say out loud very often. So so for the record, anyway, these two vectors are essentially as you said, steady state vectors, which means that they're their own. By definition of what an eigenvector is, eigenvectors only when you apply a linear transformation to the eigenvector, that is literally a scaling that occurs. And therefore, when you apply your system, you're going to get a scaling along the direction of the vector that you're on, independent of which one is dominant.
Okay.
That's what I was trying. I think that's now said correctly.
So earlier it sounded like you wanted
words are hard.
You wanted to incorporate the idea that dominant and non-dominant eigenvectors and eigenvalues are going to mean something when you're on one of them specifically. Now, it may contribute, like both of the vectors and both of the values may contribute to that scaling, but nonetheless, it's not really something we have to worry about in terms of like, oh, well, what's it going to be? We got to go find exactly how much, like, you already know what the change is going to be from the original system. And it's not going to specifically matter what direction or what value the other eigenvalue or vector has on it. Again, it might affect how much it scales, but it doesn't actually affect, like, anything else about the vector you are currently on. I don't know if I'm just rambling at this point, sorry.
You're fine.
Okay.
So Peach Tea had a question too about easy ways to find eigenvalues. I don't know if you want to address that or if you have like anything helpful there.
So we are going to talk about that in terms of how to get that one, right? The one that we have on the case above. I do just want to finish the states that we have here. Okay, so the other possibilities that we had, again, were if both of our eigenvalues have the same sign, if they're both positive, where's the flow going? Very generally.
Out to infinity?
Right, so, and this is no matter where you are. Right, both of our vectors are going to be pointing outward with some amount of magnitude. We don't know exactly how much it is. Again, we're just kind of doing this very generally. But that's going to mean that as we go further away from our origin, right, all of the possible paths are going to be moving away from our origin. And in this particular case, this is going to be a source at the origin, meaning that like everything is flowing away from our origin like that. So it is a source of all of the, let's say it was a fountain, for example. We'd have a source of water at the center, and everything is flowing away from it with some particular speed. All right, if they are both negative, then what happens?
Maybe flowing in toward the origin.
Right, and Dawn said a while ago Thank you, Don. Don had said a little while ago, if one or more have a negative sign, then it's going to be more important, or it's going to be stronger at smaller values of t. So, that is, yeah. So that's going to be true, that it's going to flow faster at smaller particular values of t. It's going to get changed a lot quicker right at the beginning. And yeah, as Don joked, this is going to be a sink. Everything is moving in toward this particular point. This is where we get the phrases, I mean, just literally the sink, but also talking about heat sinks and other stuff like that. This is the place to which all of this particular thing is flowing. Right? In the case of whatever it is, particles or anything like that, we might have a black hole here at the origin. It might be water flowing into a low point, right? The drain on the same fountain that we were talking about up above with the source. Whatever we want to call it. Also, the one that had the opposite signs. With all of these phase plane flow lines, our possible solutions, moving around the origin point like this. What do we call the origin point itself?
Sure.
So if you have a particular curvature that is going to be negative one way and positive the other at the same time, anybody know topology?
A little.
Yep, Femvox, you got it. It's going to be a saddle point. So in one particular direction it's flowing toward, and the opposite direction it's flowing away, and so we get this saddle curvature behavior. Same sort of idea as like an actual saddle shape, but this one is not particularly in 3 dimensions. It's just showing us the way that usually we're talking about a essentially 2-dimensional flat plane, how particles would move across the surface of water or what have you. Okay. And what happens with complex conjugate eigenvalues?
So these typically are with relation, like they have some kind of elliptical path or circular path that happens because these are exponentials to an imaginary. They'll end up being multiples of sine and cosine, and they'll turn either circular or elliptical depending on circumstance.
Yep, so typically if we're going to get something that's pure imaginary, then we end up with some sort of circular path. If we end up with
something real in it,
yep,
then it does some spirally thingy.
Yep.
Right? Depending, and the direction is going to depend on the nature of our exponential. So if our exponential, or the real part, is positive, you'd expect some kind of outward movement, and then inward movement would happen with a negative exponential.
Yep. And I don't remember exactly what determines the direction of spiraling, but we can talk about that when we get actually into some of these individual problems. Right. And so the weird one ends up being this, like what happens when we get two overlapping or repeated eigenvalues. And again, we'll talk more about this in just a little bit. Let's see if I got a picture right here.
Well, and this sort of depends on the eigenvectors, right? So whether you have a full set or not. You have some different behavior.
Yes, so there's still two major behaviors, right? We end up with either lambda is going to be positive or lambda is going to be negative. But typically what happens is you have your vector, whatever it might be, and then from this individual point, and I think Femvox actually did say it before, this is either going to be a this is either going to be a sync point or a source point, but then there is, like, you know, along the along the eigenvector itself, you end up getting the straight lines naturally, and then there ends up being like a second direction, which I think is going to be orthogonal to the eigenvector itself, which is going to be sort of like you're going to infinity through your exponentials. Now, I could be wrong about that. It's been a real long time since I did this, but and I think I have come up with several like different possible ways to do this. So we'll maybe do a little more exploration later. So lambda repeated is greater than 0. We get something like this. And the one I have here looks like this. All the stuff is going inward as usual. And then I've got one that actually like curves around crazy like that. So again, this could be exaggerated, but like I feel like I did my homework when I made these notes. Right, so on this particular we get this kind of spiral sync, which works in like this, but at the same time, you've got a particular vector that is going to be your eigenvectors pointing directly in or directly out. Okay. Why don't we take a short break and get up and stretch? If everybody is okay with that.
Cool.
And we'll be back in 3 minutes to do the actual algebra and get our actual get our actual eigenvectors for the values that we found just a few minutes ago. So 3 minutes, everybody. Be right back. Thank you so much. All right, and we are back from break. Next question. How far through my notes are we? Cool. Nope. We'll wait on that one. Okay. So with the system that we had earlier, y prime is equal to 3, 2, 1, negative 1, x, y. So earlier we said the easiest way to figure out what the actual, well, okay, we didn't say the easiest way, but the way we were exploring earlier was we take our A matrix and we say that we want to take our 3, 2, 1, negative 1 like this, and we want to subtract lambda 0, 0, lambda, and set this equal to, set the determinant of this equal to 0 in order to make sure that we had a non-invertible eigenvector xi that we could come up with. So in this particular case, this ends up that we have the determinant of 3 minus lambda, nope, not 0, 2, 1, and negative 1 minus lambda. All right, so with that, what's this going to produce for this particular matrix?
So you take the product of 3 minus lambda and minus 1 minus lambda and subtract 2 from that.
Right, so again, doing determinant, the product of the major diagonal, subtract the product of the minor diagonal, or I think I was taught main diagonal as like the one that goes top to bottom, and then the off diagonal going the other way. This doesn't work so well if your system is greater than 2. As it turns out, we need to make a much more complicated thing, and we can talk about determinants of 3x3 systems and things like that some other time. Especially if you want to do it by hand, it's kind of a nightmare. And, PHT lingo, there is a slightly easier way to do it. So we can talk about that in just a bit. Okay, so what do we get as the product? I'll get lambda squared.
Minus 2 lambda.
Yeah, so...
And then minus 5, I think.
Negative 3 there and a positive 1 there, so yeah. Negative 2 lambda, we get a negative 3 here and a negative 2 there, so yeah. Minus 5 is equal to 0. Okay. Is that a nice one?
Well, it's the same as our 1 plus or minus square root 6 that we had before.
Right.
That is the same quadratic. So
one would hope, right?
Yeah.
Yeah. So literally the same exact thing that we had here. We're just plugging in the numbers into this quadratic and then getting the same stuff. Yep. So we already know lambda is 1 plus or minus square root of 6. Okay, now what? I'm going to change the music. Hang on. Don't want to give people anxiety. Jeez. Much better.
So, are you saying that you want to find the eigenvectors? Or...
Right? Yes.
Because then you'd have to substitute lambda, the respective lambda values in for lambda, and solve for the null space. Or solve for where that matrix AX equals 0.
Right, so really what we wanted here right, we want our x prime y prime, or vector xy prime, to be 0. So as you said, null space. Oi. Come on now. Right, where do we get something such that the the transformed particular xy or xy1 xy nope. Wow, I'm okay. Yeah, we want this one to be not particularly xy, but xy1. Or just any eigenvector, it doesn't matter. This is going to be the null space solution 2. This was our A minus lambda I equaling 0 vector. No. All that times xi. This is fine, I promise. Getting to that point of the night.
Yeah.
Okay, so earlier we'd said that we want this stuff, that particular product, to be equal to our 0 vector. Okay, so that's where we're going with this. So now we say, how do we make that happen? Well, we can multiply all this stuff back out, but quite frankly, that's going to be kind of gross. So, most of the time, what we're going to be doing here is to solve by plugging in each of our lambda eigenvalues one at a time. So let's just do the positive one first for sake of argument. So 3 minus 1 plus root 6, 2, 1, negative 1 minus 1 plus root 6. And we want that, when multiplied by our xi vector, to equal 0 and 0. So in this particular case, often what we do is we augment the matrices. And we can solve this system of equations using matrix operations rather than going in and doing the strict algebra for it. This is just algebra 2 stuff, so like it's a system of equations, super easy. The only thing that gets in the way at this point is there are going to be square roots. Okay, so we get 3 minus 1 is 2 plus, nope, minus. 2 minus root 6, 2, 1, and negative 1 minus 1 is going to be negative 2 minus root 6. Augmented with 0, 0. And just as a reminder, right, what does that really mean? Let's take that one out. What does that really mean? Well, it's 2 minus root 6 times x1 plus 2y1 is equal to 0. And again, simultaneous equation, 1x1 minus plus parentheses, negative 2 minus root 6 y1 is equal to 0. So again, you could do this system of equations pretty much any way you want. There is a fun, real fast way in your calculator. We'll give you the name of that in just a minute. What we would like to do is to empty out, better way to put it, what we would like to do is end up with the identity matrix times, I need to stop that. Same thing I did before. All right, x1, y1 is equal to whatever numbers these are going to be here. So in order to get our identity matrix, this is going to be a 2 by 2. We need 1, 0, 0, 1 as our goal, times x1, y1 is going to be equal to those two numbers, which of course will be the solutions to our system of equations. All right, how do you want to go about it? Swap the rows first. Absolutely, Don. Thank you so much. All right, so for your row operations, what you are allowed to do, 1, you may add a linear combination of the two rows together and replace either of the rows. You may also swap the rows, as long as you're swapping everything all the way across, including the stuff on the augmented side. In this case, they're both 0, so like it doesn't matter. But and again, the goal is to get a 1 in the top right, that's the left, top left corner, and a 0 underneath it, and a 1 in the bottom right corner, and a 0 above it, so that you only have 1 of each thing. Again, identity matrix. Yep, and that was, I was thinking in my notes it was going to be like, oh yeah, we'll just multiply by, no, I also swap the rows first, so. Woohoo! Nasioma, how's it going? All right. So at this point, it would be real easy to get rid of the thing that's underneath it. So here we're going to take row 2 and subtract off 2 minus the square root of 6 times row 1. Moogle. Nice. Right, and then we're going to replace row 2 with that solution, or with those values. So the first row is not going to change at all. We still got a 1, negative 2 minus root 6, augmented with 0. And underneath it, we now have row 2 minus, so that's 2 minus root 6, minus 2 minus root 6 times 1. So that's going to just be 0 there. Cheap viewers. Thank you, Don. As you all say, right? We don't want the cheap ones. We want the awesome ones.
Exactly.
Okay, so second one, slightly harder, not too bad. What we're doing here is we're going to take our 2, which is, again, row 2, and then subtract off 2 minus root 6 times the stuff in row 1. So all that stuff multiplied by this stuff here. 2 minus root 6 and negative 2 minus root 6 are... Just keep doing that, it's fine. Right, we may not actually notice too much, but this is just the difference of squares. In this case, it's the first thing that ends up switching its sign rather than the second, but whatever, it's the same thing. So we end up with the difference of squares here is negative 4 and a positive 6, and then the cross terms are going to add up to 0. So we end up just with 2 for this part here. And that's now going to be a 2 is the row 2 part, minus 2, which we just got from 6 minus 4. So we end up with a 0. Now at this point, some people might decide to panic. And that's understandable. How do you all feel?
Unpanicked.
And why do you feel unpanicked?
Well, because that's a real number. And because, frankly, the last two, the row, one of the rows eliminated.
Mm-hmm.
That's sort of good. Which means we get to choose a direction, or we get to choose one of the variables. We have a free variable system. And, yeah.
Yeah, I think when I first saw this, I was more in the panic mode because I was so used to the Algebra 2 way of thinking where we're like, okay, if this happens, this now means that we don't have a system of equations anymore. And so that means that there is not one unique solution, but actually that works extremely to our advantage. All right, so what do we want to do? So I would like...
I was going to say just move something over.
Yeah.
X1 equals, just 2 plus root 6.
Swap the sign, right?
Y1.
It's just...
Exactly.
Yep. Silver, yes, has also been called a unique solution. How's it going this evening? Right, so at this point, we're saying that, well, x1 is just going to be the same as 2 plus root 6 times y1. Yeah, the music just keeps going creepy. The Haunted. Hey, this one's called Caffeine. There we go. The music is also panicking, yes. Busy day at work, nice. Usually. Okay, so right at this point we can say, well, if we work with this and say, again, x1 is now a constant multiple of the other term that was in here, then this creates, as Zach was saying, it creates a free variable. Or we could also say that this just creates our eigenvector for us. We can let y1 be equal to 1. And so x1 is going to be equal to 2 plus the square root of 6. Alright, and that could be equal to c1.
Oof.
Thank you, Silver. Okay, so now what?
We've got I guess we know now. We know direction, we know magnitude. So we know like the steady state, right?
Have a direction, yep.
Right. Oh, I see.
Well, we know what direction that is because we know that it's pointing, that the vector is pointing in the direction of 1 plus, or root 2 plus root 6, 1. We can just plot that vector, and that would be our positive sloped vector. If I'm not.
Which was approximately, we said?
Like, I think it was like 2.2, but that doesn't seem.
I think that was negative 2.2.
Oh, okay.
The other one was in the neighborhood of 4, if I remember correctly.
Almost.
It's like 4 to 1. Yeah.
So it was 0.4 to 2. And so we worked that out. If we plotted that as a slope, it was going to be about 0.2. And again, that was a very approximate solution based on a picture. So the actual value here, if we make this the change in y is 1, and the change in x is 2 plus the square root of 6, we get 0.22474487. So 0.225 is close enough. How do you think that works? Reasonable?
Seems reasonable.
Right, for an estimate that we did off a picture, yeah, alright. A little bit more than a tenth off, so. Alright. How do we get eigenvalue 2?
If we use the other eigenvalue?
Right, so we said here we're going to get 3 minus the other one, which is going to be 1 minus the square root of 6. 2. Come on now. 1 and negative 1 minus parentheses 1 minus root 6. Augmented with 0, 0 in exactly the same way we did the other one. Alright, what do we get?
Essentially the conjugate, in some sense, of what we had before.
Yeah, so real close. Not 100% the conjugate, right? But
yeah. It's pretty close.
Right, and then again, same deal as we did before. Swap them first. Just make your life a lot easier. Oops, not root 2. This is not the sum of angles formula. And 2 plus square root of 6 and 2. And again, same deal here. We're going to take row 2, subtract 2 plus the square root of 6 times row 1, and then put it back into row 2. So again, 1, negative 2 plus root 6, augmented with 0. And on the lower, we should get
all zeros.
Right, and again, if you want to check us on this, absolutely go for it. But this is the point, right, is that we actually want our C eigenvector to show up as something that does not have a unique solution. That this is going to have multiple solutions along this particular line. Right, so this is a dependent solution, going back to Algebra 1 terms. So C2 is going to be, again, we can extract all of this stuff. Ugh, not what I wanted, but all right. This is 1x1, or 1x2, sorry, plus parentheses negative 2 plus root 6. y2 is equal to 0. Again, set it up so that the other side here is going to be 2 minus root 6 y2, and let y2 be equal to 1, because that's way easier. And if you decided that you didn't want to do that, what would happen?
You'd be pointing in the same direction.
Right, because?
Because the ratio of x2 to y2 is constant. x2
right.
over y2.
So, however you're doing it, it doesn't really matter what numbers you're putting in there, because you're always going to end up getting the... right, I mean, not literally, it does not matter. But as long as you're plugging a value in for y2, it doesn't matter what value you're plugging in, as long as it's not what?
Well, it's not 0.
Yeah. Don't let it be 0, because that doesn't work. Okay, so this means that we've got our... You already said linear combination of C1 and C2 need to be in here somehow. So how do we do linear combinations?
Well, it's that solution, so you have to include the solution associated with the sum, right? But you're going to include an exponential with your eigenvalue. Or I don't know if that's what you're talking about. Like what you're, I don't know what you're going for here, but
so when you say just like a linear combination of these things, right? What other piece needs to be in there? We'll worry about the exponential portion in a minute.
But the scalar, it's a scalar multiple of C1 and a scalar multiple of C2 summed together.
Right. And this fits perfectly with what we just said about our vectors having different values put in for y2 or for x2 or for whatever else, it's always going to end up just scaling it. So if yours is different from somebody else's, like, they should still just be off by a constant multiple, and that's it. If there's any bigger difference, then it needs to be looked into. Okay, then we said we also need the fact that we were talking about a solution to differential equations which are of this particular form, which again, we said like way back when, probably back here, right? Our solutions are changes in x and changes in y. We're going to be represented by these sums of x and y in some linear combination. So here we were saying, well, they're probably going to be exponential solutions because, just like we talked about in previous classes, whenever we had the rate of change of something equal to a constant multiple of itself, or the original value, x prime versus x, then it was going to be an exponential function of some kind. So here we're doing the same thing. We're saying, well, this should be a linear combination of those two exponential portions as well. So some e to the t stuff should be going on here. And then how do we affect each of those individual e to the t's in order to fit the model that we have? I'm being vague.
You might be a little too vague.
Okay. So we were saying that we wanted our e to the t in both of these cases to be modified in order to make sure that Dawn had mentioned, like, you know, as t gets big or as t gets small, it's got to affect the overall solution in some way, shape, or form. So
Sure, on strategy.
Right, so that's affected by the eigenvalue.
right, so we're going to take our eigenvalue, and again, we said that in the case of a negative eigenvalue, this is going to pull stuff toward the origin, and in the case of a positive eigenvalue, this is going to pull stuff away from the origin. Or push stuff away from the origin, I suppose. Okay, so this is actually going to be our overall x vector solution to our differential equation that we had all the way back at the beginning. So here we started with, again, an xy, come on, xy prime is equal to 3, 2, 1, negative 1, multiplied by xy. And now we're saying that this whole thing is going to be this vector representation up top, or we could also make that xy is equal to a constant multiple of our eigenvector 1, which was 2 plus root 6, 1, e to the lambda 1 was 1 plus root 6 t plus c2 2 minus root 6 1 e to the 1 minus root 6 t. All right, so that representation should hold as well. If we take the derivative of all of this stuff, I mean, good news, it's just going to take down our 1 plus root 6 and our 1 minus root 6 respectively and multiply those out front. And then that's going to multiply through with each of these values in the vector. And then we can see what happens as we combine those and whether or not that does, in fact, get us 3 of our top row plus 2 of our bottom row for the top row, and then one of our top row minus our bottom row for the bottom row. All right. Questions? Other things you might want to highlight?
So I guess it's important to point out that this represents actually an x solution in terms of t and a y solution in terms of t. That might be helpful to at least make sure it's clear that we actually have two solutions in a way. That they're parametric equations in terms of x and y, or in terms of t with x and y determined in terms of t.
Right. So our independent variable, we had talked last stream, a week and a half ago, about the fact that our xy matrix is parameterized over t. So even though there's no t in the original differential equation, we're still saying that x and y individually are functions of t in order to make all of this work in the first place.
Right.
And that really is like, no matter whether t is a real thing in this problem or not, we can just say like, oh, we're parameterizing it over time, even if it's not literally time. On Wednesday, we're going to talk a little bit about some applications of this. And where is it? There it is. Right, we're going to talk about how to make sure that a particular solution set is valid. So we're going to talk about the existence and uniqueness ideas that we had in our first order linear differential equations, which are just using one equation, and so now we can extend that to systems of equations. We'll also check whether or not, in order to make sure that this is a solution exists, we're going to check what's called the fundamental set of solutions and see what happens from there. There is also, and I think I tried to jump the gun on my prompt for number 5, but we're also going to look a little bit at like, what does it mean to have a portion that is just a function of t. So that may be next week, but nonetheless, we'll figure out exactly when things
like an inhomogeneous system.
One more time.
That would, like an inhomogeneous system.
Yes.
Is that what you're talking about?
Yes. So non-homogeneous. It's the way that I learned it, so it's just gonna get stuck there. So the non-homogeneous systems do have an additive portion which is based on t alone, which does include constants that are non-zero. So like, what does that actually mean? And we'll get into that when we do that sort of stuff. So I think I'm gonna let you all go here, and I will continue a little bit just to prove here that this is in fact the correct solution to the above differential equation.
All right. Well, thank you so much for hosting.
Yeah, thanks for coming. So happy this all worked out.
Much appreciated.
Yeah, thank you very much.
Take care, Obi, and take care, Zach.
You
Yep.
too.
See
Thank you,
you,
Stuki. Thank
I'll
you,
see you
Obi.
when you two are live next, and/or when we come back here. So.
Yep.
Okay, so we're saying, oops. Just make sure that we disconnected that. Yeah, cool. Or something. My differential equations class is now showing up as possible. Something that I can now start. Thanks so much, Discord. Okay. So we wanted to double check with this one. Is it true that when we actually take the derivative of this whole solution that we do in fact get the original setup that we had for the differential equation? So we're going to go through this real quick here and say, all right, fine, xy prime is going to be equal to. As we go through, we're going to check to see whether, what is it that we need to do to actually take the derivative. So first of all, the c1 and this vector are just constants. Ta-da! So we don't have to do anything at the moment with these two bits. You could just say, that's it. All right, then we take the derivative of the e portion, which is itself times the constant up top. So we get a parentheses 1 plus root 6 times e to the 1 plus root 6 t. Plus c2 times our eigenvector 2 minus root 6, 1. Again, multiply by 1 minus root 6 times e to the same 1 minus root 6 t. Okay, so what are 1 plus root 6 and 1 minus root 6 multiplied by, respectively, 2 plus root 6 and 2 minus root 6? Okay, not terribly difficult, so 2 plus root 6 multiplied by 1 plus root 6, all positive values. So we get 2 plus 2 root 6 plus root 6 plus 6 when our roots come together. So now we get 8 plus 3 root 6. Okay, and 2 minus root 6 multiplied by 1 minus root 6, 2, and that's going to be a minus 2 root 6, that's going to be a minus 1 root 6, and that's going to be a plus 6. So 8 minus 3 root 6. Alright, well, somewhat anticlimactic. Maybe I should have known that offhand. Alright, xy prime is going to be equal to c1 times now the vector 8 plus 3 root 6 and 1 plus root 6 down bottom here. And e to the 1 plus root 6 t plus c2 times 8 minus 3 root 6, come on, and 1 minus root 6. E to the 1 minus root 6 t. Doesn't look like much, but now we can go back and say, based on the original, right, we've got this stuff here, xy all primed is going to be equal to the original xy times our transformation matrix 3, 2, 1, negative 1. So next question is, are these two things equal to each other? So this is going to be 3x. Silent Night again? Really? I got nothing against Christmas music, but like after Thanksgiving. Alright, so 3x plus 2y. And our second one here is going to be x minus y. So now we have to kind of move this stuff around and figure out, alright, is this going to be the same as the stuff that we got up above? This might be a little trickier than I wanted. It'll be fine. Alright, so 3x, the original x, is going to be C1, right, times 2 plus root 6 e to the 1 plus root 6 parentheses t plus C2 times 2 minus root 6 e to the 1 minus root 6 t. Reach the end of the thing. Ah, well. 1 minus root 6 t. Okay. Plus 2 times the quantity. Alright, sometimes this gets a little tedious. It's okay. Y is going to be equal to, that was C1 times 1 e to the 1 plus root 6 t plus 1 C2 times e to the 1 minus root 6 t. And the lower is going to be 1 of that same thing. Hey, you know what? Can I just copy this? A. Yes, I most certainly can. Saves me a little time. Okay, minus 1 of the same as above. There's that one. All right, can we do this by examination? Yes. Okay, so we have here 3 times 2 of these things. And over here we have 2 of those things. In fact, we can do C1 times that E term, right? So 6 of them over there. It's going to be 6 C1 E 6 to the 1 plus root 6 t. Okay. Oh, 8. Jeez, man. Told you it was that time of night. Right. 6 from the left and 2 from the right. There we go. All right, and then also we have another 3 root 6 of them. C1e the 1 plus root 6 t. Well, I think that is mission accomplished, because up here we have 8 plus 3 root 6 c1 e to the 1 plus root 6 t. Right? All the pieces in there. And then we also get same deal. What about the other one, right? Our c2 e to the 1 minus the square root of 6t. Well, we have 3 times 2 makes 6 again, and then plus another 2 from the other side is going to make 8. And then 3 minus root 6 is here, so that's a negative 3 root 6. C2 with the same E. So those get combined. Right, and over here, 8 minus 3 root 6 e to the 1 minus root 6t. All right, and then same for the bottom. I don't know if anybody wants me to go through it, but nonetheless, we got 1 times 2 gets us 2 c1 of these, minus 1 c1 of those gets us only 1 left, right? 2 over there minus 1 over there. So we only have 1 left. And then we get a root 6 of those. So 1 plus root 6. And then on C2, we get, again, 1 times 2 minus 1. So 2 minus 1 is 1. And then a minus root 6 of those same. So 1 minus root 6. So we end up with a big resounding yes, those are, in fact, equal to each other. Woohoo! Like I said, these get a little tedious when you want to actually check them, but it works okay. Also, what we had done to find the solutions here, sorry, to find our eigenvectors over here, has a special function in your calculator which can do the thing for you, but of course, if you want it to do it correctly, you do have to be careful. So in this case, because we have a square root in here, we're going to just get a string of decimals. So if you're doing it in like a TI calculator, if you want to get the exact value, which includes the square root thing, then you could go over to Wolfram or something like that and type in, get me the row reduced echelon form of this particular matrix. So you'd want to take this matrix here, 2 plus root 6, 2, 1, negative 2 plus root 6, get me the row reduced echelon form, or RREF, of this particular thing, and it'll get you this. All right, 1, negative 2 plus root 6, 0, 0. And again, in this particular case, that's actually what we want. Most times when you're dealing with matrices and you want row reduced echelon form, you don't actually want that. So, for instance, if we wanted, A is equal to, let's just do 3, 2, 1, negative 1. And we want to find the inverse of that particular matrix. We already know that the determinant of this matrix is non-zero, so that's okay. We can do this. One of the ways to do this is to say, okay, what we've got is A times X is equal to Yep. Is going to be equal to I. And in fact, it can't be a vector x. It needs to be inverse. Right. So A times A inverse is going to get us the identity matrix. So if we multiply by A inverse on the left specifically, that will cause this stuff to become I inverse is equal to A inverse I. Or just I times A inverse is equal to A inverse. What we want here with the stuff we've been doing is we want to augment 3, 2, 1, negative 1 with, not with 0, 0, because that got us the particular null space matrix. What we want here is to augment it with 1, 0, 0, 1, the identity matrix. So that at the end, A inverse is going to be the matrix that we have skipped here, that we have augmented everything with. And then on the right-hand side, we'll end up with A inverse. Right here, we want to get the identity matrix. So my first move is probably going to be take row 1, subtract 2 row 2. So let's keep all of our notes in the same color. Okay, so if we take row 1 is 3 minus 2 ones is going to give us 1. We're not going to change the thing below it, right? So we're not going to change row 2 at all. In theory, you could do it all at once, but it just gets to be a burden. I don't necessarily want you to get confused at all. And for the 2 here, we have row 1 is 2 minus 2 negative 1s, so plus 2. So 2 plus 2 is going to get us 4. All right, over here we get 1 minus 2 of the things below it is going to just be 1. And 0 minus 2 of the things below it is going to be a negative 2. Okay, now we're going to do the same thing. So here we're going to take row 2, subtract row 1. And we're intentionally knocking out this 1 to make it 0. That's our goal. So 1 for augment, 1, negative 2, not changing the top, and then changing the bottom. So row 2, so 1 minus row 1 is 1, gets a 0. All right, goal complete. Our first column is now 1, 0. So we're good. The next thing is 4, and then below it, row 2 is negative 1 minus row 1, which is 4. So we need, this is going to be a negative 5. All right, same deal. Row 2 is 0 minus the 1 above it is going to be negative 1. Row 2 is 1 minus the thing above it is plus 2. So 1 plus 2 gets us 3. All right, keep running with it. Okay. Row 1, we're going to... Yeah. All right, row 2, we're going to multiply by -1/5 in order to get a +1 in the first non-zero position. Alright, and then this one, we can go either way with this. Either wait until we have fractions in here or just clean it up now. So we want to keep row 1 more or less the way it is, but then we're going to add 4/5 of row 2. Either way, you end up getting the same stuff, so whatever, it's fine. So here we get 0, a 1, augmented with -1/5 times the -1 is going to be a 1/5, and a -1/5 times 3 is going to be -3/5 on the bottom row. All right, top row. We still have a 1 in the first position because row 1 plus all the zeros underneath it are still going to be 1. We get a 4 here, which then we add a 4/5 of -5 is going to be -4. So 0. Oh hey, look at that. Right, we've got the identity matrix, so now everything on the right hand side is going to be our actual A inverse matrix once we finish this row. So here this is going to be row 1 is 1 plus a 4/5 of -1 is going to be 1 minus 4/5. So 1/5. And a -2 plus 4/5 of 3 is going to be 12/5 minus 10/5. So we get 2/5. Alrighty, so that should be it. Right, we could double check by doing 3, 2, 1, -1, multiply by 1/5, 2/5, 1/5, -3/5. Right, unless I messed up somehow, which is always possible. First row, first column is going to be a 3/5 plus a 2/5. So that's a 1. First row, second column is going to be a 3 times 2/5 is 6/5, and a 2 times -3/5 is going to be a -6/5, which added together gets us 0. Second row, first column is a 1/5 and a -1/5, so that's 0. First row, second column is a positive 2/5 and a positive 3/5 after you do the thing. After you multiply the values together, and yeah, you get the identity matrix. So yep, this is our A inverse given the A that we had, 3, 2, 1, -1. Cool. But I hear you say, what about a 3x3 matrix? Because everybody wants to know, how do you deal with a 3x3 matrix? Sure. Okay, so if we have here matrix B, and if we want to know what is the determinant of B, all right, the way to do this always gets a little bit tricky, and a lot of people hate it a lot. I mean, obviously, you could just use your calculator. But then, if you're going to not cheat about it. So if you're doing it by hand and you're going to actually do it out, there are several different ways to work on it. So one is that you take a kind of checkerboard pattern of pluses and minuses. Oops, not there. And you say, okay, what we're going to do is pick a row or a column. Completely up to you. Does not matter which one you do. We're going to do 3 times the determinant of the 2x2 matrix that's left over. If you were to get rid of this row and this column. Again, our 3 is going to be sort of the pivot point on this. Anybody who teaches linear programming, I apologize. Only slightly. So the determinant of the 3x3 matrix is going to be 3 times the determinant of the little 2x2 matrix that's left over when you draw in a cross through the row and column of the 3, what the 3 belongs to. Okay, and then we look over here and we notice that this is a -2. So we put a -2 in front of, again, the row, and cross out the row and column that the negative, or that the 2 belongs to. And then write in the remaining 4 items. So 4, -4, 3, -2. And then do the same with the 5. We get a +5 times the determinant of the 2x2 matrix that's left over when we cross these things out. So 4, -1, -2, 2. Yeah. Now, me personally, I don't actually like this as much as another method that I found, but I'll deal with that in a minute. This is going to be equal to, okay, 3 times the quantity. This is going to be main diagonal is -3 minus off diagonal is -8. So -3 plus 8 is going to be a 5. -2 times 12 minus 8. It's going to be +4. Plus 5 times 8 minus 2. 6. Is going to be 15 minus 8 plus 30. 45 minus 8, 37. Right. So the determinant of B is going to be 37. That's going to be a really nasty thing to find the inverse of, by the way, if we try to do it. Alright, I don't like this pluses and minuses thing. I hate it. Instead, what I'm going to do is I'm going to use the exact same stuff, 3, 2, 5, going across. And I'm still using a determinant of the remaining 2x2 that's left. However, I don't care about its position. What I'm going to do is I'm going to draw a line through the row and column of each of its positions. Now I'm doing number 2 here because this is the one that's actually different. The top left corner of this matrix is here. and it wraps around to get the right-hand side of this matrix. So if I want my 2 to be the pivot point that we used for the middle one over here, unlike the original one that I showed, which gets 4, -4, -2, 3, this is now going to be the other way around. It's going to be -4, 4, 3, -2. Okay, so -4, 4, 3, -2. The 3 and the 5 will end up being the same, although... No, they are exactly the same. It's fine. Because what I do is I say, okay, my 5 is here, and the top left corner of this matrix is going to be here, but there's no number, so we wrap around, and it's the 4. So it'll be 4, -1, -2, 2, which is the same as what we see here. And 3, when we cross its row and column out, we still get -1, -4, 2, 3. On a bigger one, if you're trying to do like a 5x5 matrix, I don't recommend it. Then you would look at it and say, oh, this does work. We can make it, in fact, it will be different, but the eventual solution that we get is going to be identical to what we get with the original version. All right, so why does that work? Why does this thing become negative by switching the columns? Right, this is going to be a +2 times the quantity. Oops, not determinant anymore. This is going to be the main diagonal is going to be 8. And now our off diagonal is going to be 12. So now it's 8 minus 12, which is -4, which is going to be a -8 total. But that is what we have back here. Right? A -2 and a +4. So now we just have it the other way around. Now it's a +2, but a -4 on the inside. Alright, like I said, these other ones don't change at all. It's just going to be a 3 multiplied by a -3 minus -8. So we're still going to get a +5. And +5 times, here it's 8 minus 2 is still a 6. So we still get a 30, we still get a -8, and we still get a 15. And so the result is still 37. But I can hear you say, what if we tried a different row? Okay, fair enough. Let's do the middle row, because this is going to be the most inconvenient. Right? Determinant of B is going to be equal to, I had this as a 4, -1, -4 as my 3 coefficients. 4, -1, -4. Okay, let's erase these here nice and carefully so we don't erase anything actually important. Right, so never mind this checkerboard pattern nonsense. Boo. That was a -1. Okay. Okay, so we're going to use this stuff. Oh, that can't be allowed. Huh? Okay. It sounded really dangerously close to Final Fantasy VII battle music. Okay. So the way I'm doing this is I'm saying, okay, we're going to start at 4 as our like pivot element. We're going to cross out all the stuff in its row and column, and then the top left corner of this matrix is going to be that 2. So 2, 3, 2, 5. Okay, -1, same deal. So for the -1, now I take this and go lower right of that. We start with a 3, and then we go around to a -2. And then when we go down, we're actually just going to go right back up to the top there, and we get 5 and 3 as our next stuff. So 3, -2, 5, 3. Right, and again. Start with our -4 and go down and left of it. Again, this doesn't count. Down and left of it is going to be a -2. So -2, 2, 3, 2. So the more astute of you will notice we're doing the same multiplications. It's just in a slightly different order. So here we get a 4, and here we're going to get a 10 minus 6. It's going to be a 4. Here, this actual multiplication is slightly different, but unless I'm completely wrong, this should fix itself over time. It's going to be a -1 times 9 minus -10. So we should get a 19 for that one. And here we get a -4 minus 6. It's going to be -10. Right? Okay, phew. 16 minus 19 plus 40. So here we get a -3 plus 40, which is 37. Phew. I was actually almost nervous there for a second, thinking that it might end up not working out 100% the way I wanted it to. Like if I made some sort of mistake in where I put numbers or things like that. But, nah, we're good. Ought to trust myself more. So doing determinants of 3x3 matrices, I'm much more prone to using the portal method, which is that I'm just going to pick a top left element, and then I'm just going to like use a torus, essentially, wrap around and find what the other elements are to its right and below it. And if it wraps around, it wraps around. I'm not too worried about it. I'm okay with that. All right. Does anyone have any questions? And whether that is Yep, whether that is particularly math or if you have any education questions, anything like that, be willing to talk a bit about whatever you feel like. Is there anything else that I was going to do here? Finding the inverse of a 3 by 3 isn't really any harder. It's just scaling up, finding the inverse of a 2 by 2 by using row reduced echelon form. So I'm going to do the exact same thing and say, all right, this is going to be, right, 3, 2, 5, 4, -1, -4, -2, 2, and 3. And I'm going to take those things and augment them with a 3 by 3 identity matrix. And then solve for identity here. Again, in this case, it's not too bad. We'll take row 1, we'll add to row 3, and then store back in row 1. We'll take row 2 plus 2, row 3, and store back into row 2. And yeah, be good enough. We don't have all even numbers along the bottom or anything like that, so it's just going to be slightly awkward. I don't want to do halves yet. It'll be fine. Screw it, we'll go up. This is terrible, I'm sure. Alright, row 1 plus 2 of the bottom row is going to be 1. Plus 2 of the bottom row is going to get us 6. Plus 2 of the bottom row is going to get us 11. Augmented with 1 plus 2 of the bottom row, 0 plus 2 of the bottom row, and 2 there. So 0 plus 2 of the bottom row gets us 2. Going down to the second row, row 2 plus 2 of the row below it is 0. -1 plus twice 2 is 3. And -4 plus twice 3 is 6 is 2. 0 and 0. 1 and 0. And 2. -2, 2, 3. 0, 0, 1. Alright, in order to eliminate the bottom row, I would like to take row 3 plus 2, row 1, put it back in here. And second row, we could do some stuff, but let's just leave it for now. We can, however, take row 1 and subtract 2 of row 2 to get rid of our second item. Alright, so use our 1 to get rid of the -2 in the bottom row, and use our 3 in the second row to get rid of the 6 on the top row. Like that. So here we're going to get 1 minus 0, still going to be 1 in the first position. 3, nope. 6 minus twice 3 is 6, is 0. And 11 minus twice 2 is 4, is 7. Alright, row 1 is 1 minus anything else underneath it is still zeros. Here we get 0 minus 2 of the row below it. And 2 minus 4 is going to be a -2. Alright, didn't change second row. Third row, -2 plus twice 1 gets us 0 result. Bottom row is a 2 plus twice the top row is 14 total. Ugh. This is where things start getting fractional. Let's see. Bottom row is 3 plus 22 is going to be 25. Yikes. 0 plus 2 is 2. 0 plus 0, still 0. And 1 plus twice 2 gets us 5 total. Okay. Leave row 1 where it is for now. We're not going to use this at all. This is where it becomes, like I said, slightly a problem. It's fine, it's just annoying. We could do literal fractions here and say that we're going to get row 2. No, we're going to take row 3. We're on row 3. So row 3 minus... Ugh. ODEs! Hey Fizzbuzz, how's it going? So, class time is officially over in terms of doing ODEs. However, if you have any other math type questions, feel free and ask. We're doing some matrix type stuff because we were dealing with first order linear systems of differential equations, and we ended up getting matrix solutions. So I wanted to do some extra, you know, algebra type stuff that people may or may not have seen before, to kind of get people comfortable. Gone pretty well? Nice. Happy to hear. So we could do like 4 times row 2 to just get it closer. And since I'm doing it by hand, like, I don't really care about how long this is going to take me. That's a weird thing to say, I'm sure, but... Right, we're going to leave row 2 where it is. 3, 2, 0, 1, 2. Alright, so take 0, subtract 0. Cool. Take 14, subtract 4 3s, so that's going to leave us with 2. Take 25, subtract 4 2s is going to be, come on, 17. Take 2, subtract a bunch of zeros. Take 0, subtract 4, -4. Take 5, subtract 8, it's -3. Yeah, and I like, as much as I can, right? We're doing stuff with integers right now. So you know what? That's perfectly fine by me. I will keep doing stuff with integers. We'll take row 2, subtract row 3. That'll get us something nice, and that'll clean out, allow us to clean out the bottom row as well. So 107. What's your familiarity with mathematics in general, Fizzbuzz? Just out of curiosity. 0. Subtract the number underneath it. So 3 minus 2 is 1. 2 minus 17 is -15. 0 minus 2, -2. 1 minus -4 is going to be 5. 2 minus -3 is going to be 5. And we did not change the number below, or the other one. 2, 4, -3. Cool. So now we could take row 3 and subtract to row 2. 107. Augment 1, -2, -2. 0, 1, -15. -2, 5, 5. 0, 0. Woo. All right, subtract 2 negative 15s is going to be 30, plus 17 is going to be 47. Oh boy. Row 3, 2, plus 4 is going to be 6. Oh man, this is going to be so messy. It's great. All right, next question. Did I screw up somewhere? Just make sure. Not necessarily that I did, just, you know. Now we're good. ODE wizard might be overstating it, but I've done it quite a lot. Yeah, okay. I know what you mean. I ended up taking the ODE course 3 different times. And no, I did not fail it. Took my original ODEs class as a part of a class called Linearity, which involved multivariate calculus, ordinary differential equations, and linear algebra, or multivariate calc, whatever, all 3 of those in the exact same class for 12 credits stretched over a year, so 6 credits per semester. I then took the exact same class, Linearity, as a 1-semester refresher course for my master's at Johns Hopkins University, where I completely aced it because I was just like, I know exactly what I'm doing. You know, some of the other computer scientists and engineers weren't as sure about what they were doing, but yeah, it was the exact same class, just condensed into 1 semester. We use this Krasik book, which is, well, it is as it sounds. It's pretty crazy. There we go. Yep. There we go. Our original class at the University of New Hampshire, slightly different, used the 3 books that came with the 3 separate classes. So we had the Multivariate by Stewart. I think I got rid of the other 2 because I had the Krasik book, and it's like, you know, it kind of encompasses the other 2. Linear algebra, I want to say it was another famous one, as famous as Rudin is for, yeah, Krasik. As much as Rudin is for real analysis, it was like this particular author for linear algebra, and I don't remember what it is. And then ordinary differential equations was the gold standard, of course, of Boyce and de Prima. -4 minus 2 5s is going to be a -14. And -3 minus 2 5s is going to be a -13. Yeah, I do use it, especially for like the fact that it has so many good application problems. You need an application problem, go take it out of that one. Like, it's perfect. Okay, so we're gonna take 1/47 of row 3 and put it back into row 3. We're going to take row 2 and add 15/47 of row 3. As it stands now. It's going to be perfect. All right, and then we're going to take row 1 and subtract 7/47 of row 3. 1, 0, 0. Ta-da! That's the easy part. 0, 1, 0. 0, 0, 1. Cool! Alright, bottom row is super easy. 6 47ths. Negative 14 47ths. Negative 13 47ths. Easy. Alright. Now we get to the part that gives us all nightmares. So. Row 2. So we get a negative 2 plus 90 47ths. This is going to be a negative 94 plus 90 is going to be a negative 4 47ths. Interesting question. Why did I get a 37 on all of these determinants? And a 47. That's giving me slight anxiety. Did I do this wrong? No. Doesn't look like it. Doesn't look like I copied anything wrong, so we'll just go with the process. Alright, second one. 5 times 47 is going to be a 235. Oh, man. 235 minus 14 by 15 is 15 squared minus 15. 225, so 210. Negative 210 plus 235 is going to be a 25. 25 47ths. And please, if anybody sees a mistake here, definitely correct me. And that's also a 5. That's a 13, though, this time. Minus 30. 225 minus 30 is going to be a 195. That's going to be a 195. Ooh. Yep, minus. And 235 above it. Okay. 40. 47ths. Top row. Alright. 1 minus 42 47ths is going to be a 5 47ths. Negative 2 plus 7 times 14 is 49 times 2 is 98. So negative 94 plus 98 is going to be a 4 47ths. Okay, and same deal. It's a negative 94 plus 13 times 7 is going to be a 91. So negative 3 47ths. Not sure I actually believe this, so we'll go over to alpha. Matrix. of the way. Alright. 3, 2, 5. 4, -1, -4. -2, 2, 3. Yeah, see, 37. Where did I get a 47 from? Well, shit. That's bad. Oh, man. So 4 minus 1 is 3. 6 minus 4 is 2. Something to do with this term right there, that 3. Somewhere along the way. Got really screwed up. Row 1 plus 2 of row 3. Right, so 6 plus 5, 4 plus 2, negative. Uh-huh. Yep, that would be it. That's supposed to be a -1. Cool. That's terrible. Oh no. Alright, we'll just do this. That's gonna mess up everything though, still. Negative row 3 plus 2 row 1. Sure. It's still gonna mess everything up, but at least it'll be slightly isolated. No. Okay. That's negative row 3. 2 of those. So 12, this makes that 10. Alright, negative row 3 plus twice this is going to be 22. Minus 3 is going to be a 19. Plus twice that, plus twice that. This, negative this, plus twice that. It's going to be a 3, not a 5. This is the problem. Playing around with all sorts of stuff like this. Eventually, you just end up getting creamed completely. But it is at least fixable, right? We know where the problem is at this point. Let's make it bottom row minus 3 of the middle. So that'll get us a 1. Alright, gets us a 1. Minus 3 of the middle gets us 13. 2. Minus 3. Negative 6 plus 3 is going to be a negative 3. Okay, so now row 2 minus row 3, yeah, that's not going to work anymore. So we can actually just do 3 row 3. Get rid of this thing entirely. No, we don't want that. 2. tragedy. Alright, get rid of all this. Alright, 1, 13, 2, -3, -3. Alright, take this thing, subtract 2 of the lower. So you get the 1. Alright, that gets us 2 minus 26 is going to be a -24. 2 of the lower is going to be a -4. Subtract 2 of the lower is going to be a +6. Makes that a 7. +6 makes that an 8. Okay. Well, I need to get rid of that anyway. Okay. Row 3 minus row 2. Alright, 0, 0. Again, this is going to be a -24. It's going to be -4, 7, 8. Bottom row is going to be row 3 minus row 2 is going to be plus 24 is 37. There we go. Alright, so I mean, we knew that the determinant here was 37, so in theory, if you know anything about inverses, it's, 1 over the determinant of the matrix times a whole bunch of other stuff. Row 3 minus this is going to give us 6. Row 3 minus that is going to be -10. Row 3 minus that is going to be -11. Okay, so row 3 times 1/37. Row 2 plus 24/37. Row 3. Row 1 minus 7/37. Row 3. Not row 1. That would not work. Just for the record. And if anybody is here to see a mathematician not make mistakes, I gotta tell you, you're in the wrong channel. Of course, I think pretty much everybody's gonna say the same thing. Alright, -10/37. -11/37. The difference is whether or not we can figure it out and how fast. Okay. Let's try this again. So this stuff is no longer relevant. Alright, 6 by 37 is going to be 180, 236. So 236. Okay. -4 times 24 is going to be a -96. Okay. -140. That doesn't sit right. Something's not right. No, that was right. This doesn't not right. Okay. 6, -10, -11. So we got the bottom row. That's good. What happened? Oh. No, it's 24 times 6, not 24 times 4. There we go. So it's not 96. right? And it's not 236 either. So it's going to be 4 times 37. The existing one is 120, 148. And that's going to be a negative. Plus 24 times 6 is going to be 120, 144. Positive side. Gets us a negative 4 37ths. Yes. Okay. Got it. That makes much more sense. Okay. So then we've got a middle thing here. Got to do the same thing. So 7 times 37 is going to be 210, 259. Right. And negative 10 times 24 is going to be a negative 240. Which leaves 19. 37ths. Verified. Cool, cool, cool. Okay, next one. 8 times 37. 7 times 37 was 259, so 8 times 37 is going to be 296. And going the other way, negative 11 times 240 is 264. Alright, so that's going to leave a 32. Yes. Alright, up top. Row 1 is a 1. So that's 37 37ths. Alright, 37 37ths. Minus 6 times 7 is 42. So 37 minus 42 is negative 5. 37ths. Oops, I went the wrong way. Yes, it's a negative 42. No. Hang on. Take what's in row 1 and subtract 7 times what's in row 3. Divide by 37. Alright, did I miss a sign on the 7? Also possible. Yes. Because the 1 should be a negative. But if that was the only change, right? Then all the rest of this stuff should be fine. Should just be that the 1 needs to carry negative 1 all the way through the end. Sure. You know what? Let's just do that. There we go. Ta-da! Now this is a plus. Now this is a plus. Okay. So we get a -2 times 37. It's going to be a -74. And here a -10 times a -7 is going to be a +70. So it should be a -4, which makes it a +4. Bingo. And last one. So we get a -2, which is again -74, plus 11 times 7 is 77. So 74 and 77 are off by 3. And that one should be a negative after all said and done. Yes. There we go. It's relatively harmless. Alright, there's B inverse. Oh, goodness. Alright. Anybody have any further questions that you'd like to ask? Interesting things you want to talk about? I probably rolled right through an ad at some point. I must have. I don't think I got an alert. That bothers me. See, we got paleontologizing is on. Painting pirate is fun, but we're on an academic night. Science is on for Microscopy Monday. Dr. Gold's on. SAT practice. Alright. Gonna head over and see Dr. Gold. I hope everybody has a good rest of your Monday or start of your Tuesday, whatever is going on for you. I will be back on Wednesday, certainly, for differential equations. I will be back on Friday with Dr. Gold. I think likely just on his channel, so Actual Education, which we're about to raid. If you have not yet followed his channel, please do so. It's pretty great. And I will be on Dr. Gold's channel on Friday doing a podcast. So we will be over there hanging out with everybody. Hope you all have a good one and get in on the SAT prep thing that he's doing, because you get to get points and prove how awesome you are at SAT math. All right. Hope you all have a good week, good day, good couple of days, good week, whatever it's going to be. And I will see you later. My name is Obi-Wan Pez. This is N Simplex Pachinko. Have a good night.